So a little bit about me. Most recently I founded Vivid Cortex. Before that I was at Percona and I wrote High Performance MySQL, and Ben and I were just reminiscing about the nostalgic old days of Perl scripts and SQL Server and shared experiences and things like that. So I've been around for a little while and wrote some open source software and books and blogs and things like that. And one thing led to another, and here we are. So my Twitter, my email, everything. Contact me if you want. I'll happily give the slides. I don't know if they'll be posted, but I always say slides will be posted because people often ask. So observability. A lot of people have been talking about observability, and for everybody that talks about it, I often hear or see responses on Twitter, things like that, like, people can't say monitoring anymore, that monitoring is a tired old word, they've got to say observability like it's the new shit. What does this mean? Observability, why wasn't monitoring good enough? And I get that. Every now and then there's a new buzzword and people start using it, and other people are like, why is this new buzzword different than the old thing? Haven't we been doing big data for a long time before we called it big data? And all of these things come in cycles. And although that's true, that observability, a lot of people are talking about observability as basically a synonym for monitoring. A lot of the people that you're hearing talking about observability are talking about something really different. And there's value in it. And so I think it's worth digging into that. There's a lot of sort of the background and the underpinnings of how we do things and why we do things the way we do. That's worth talking about. And so that's my goal, is today just to talk about, like, what is observability? What are the why is it different than monitoring? What sets it apart? And what does it rely on? How do you actually get observability? How do you create a service in particular that's highly observable? What are the signals that you get out of it that make it observable, and what can you do with those? So the first thing is that observability often will be used as a synonym of monitoring, but it's not really. Similarly to how people will talk about SRE, and they're really just talking about sysadmin, because they haven't kind of figured out what SRE means to them. But there are people for whom SRE is really something quite distinct from system administration, right? And there are people for whom DevOps really is something different. It's not just Agile under a new name, right? So observability is one of those things. And people are going to have different opinions about what it means, just like there's no single definition of DevOps. There's no single definition of observability except for mine. Mine is the only one you should listen to. And you're going to hear people talk about it different ways, but that's fine. So I'll explain to you how I think about it, and how, when I have conversations with other people whose opinions I respect and who I think are kind of on point and really onto something, how they're using it, what they mean by observability. So one thing is, what observability is not. Similar to DevOps, DevOps is not a job title. Depending on how you look at it, maybe it is a job title. People will object to DevOps being not a job title. DevOps is not tools. DevOps is not a role. DevOps is a culture. DevOps is all these different kinds of things. Similarly, observability is not tools. Observability is actually a property of a system. And I'll talk a little bit more later about what I mean by system. It's something a little bit larger than and more holistic than what we often talk about. But observability is that property of a system that allows you to see what's going on with it. Similar to testability, operability, security, all of these kinds of things. Those are properties or attributes of a system. And so we wouldn't talk about, continuous integration as testability. Testing is something that you do to something that is testable, right? So observability is something that you do, or is a monitoring is something that you do to something that's observable. I've had a half a cup of cider, so bear with me while I sort my words out. So observability is this property of a system that allows you to look at it from the outside and figure out what's going on inside. And there's a formal definition that you can find on Wikipedia, which I don't think is super helpful, because it kind of immediately dumps you into like pseudo-scientific rigor. Observability is the mathematical dual of operability. What the hell does that mean? There's probably some really formal definition of operability that's something along the lines of Turing machines or something, I don't even know. I kind of stopped at mathematical dual. I don't think that defining observability as the mathematical dual of something that obviously has a rigorous definition I don't understand is very helpful. So for me and the people that I know and kind of we're on the same wavelength, observability is the property of a system that lets you see what's happening to it from the outside. And to do this, that system must be instrumented. So instrumentation is that characteristic of the system that exposes the telemetry, which is those signals that you can see from outside. So there's kind of like a Maslow's hierarchy of needs going on here. And analytics is taking that telemetry, what we commonly call like metrics, logs, et cetera, and making sense of that. Analytics is the action of deriving insights out of this raw data. And monitoring is looking at something and saying, is it healthy? And it's actually a testing activity. Monitoring is when you, in the present tense, you look at a system and you compare it to a definition of good or healthy, and you say, is it good or healthy? Yes or no? And potentially signal that to something else to take action. So all of these things in my mind have fairly narrow scopes, even though the scopes often get really, really bloated. For example, monitoring means everything to everybody. In some, in the monitoring industry, marketing hasn't really been able to find a different word for monitoring for any of these nuances. And so monitoring suddenly becomes kind of analytics and observability and telemetry and long-term storage and diagnosis and probably 20 other kinds of things. But for me, I think it's really beneficial to define each of these things a little bit with tighter scope so that we can have a conversation about the specifics that we're talking about. Otherwise, it's kind of like who's on first, if you know that old Abbott and Costello skit. So people will often talk about the pillars of observability. I've struck it out here and said it's actually the pillars of telemetry because what they're really talking about here is types of telemetry. And those are events, logs, metrics, and traces. And I'll dig into a little bit what each of these are. But ultimately, these are externally observable signals of system activity. And that activity comes in response to some kind of an event. An event is something that happens in your system or your system responding to something. And in most of the systems that we build, that event itself is actually a request from a user, whether that user is a human, as in the case of Wayfair, maybe searching and putting something in their cart and checking out and so forth, or whether it's another system. For example, if you have a heavily service-oriented architecture and a service calls another service, that's a user relationship between those two. And that call between those services is an event. And these events and the system's response and reaction to them is where all of this telemetry comes from. So those atomic units of something happening at a moment in time, and then time elapses and something else happens, and all of the relationship between these things is where telemetry comes from. And these are kind of the simplest units or let's call them data models of telemetry that are commonly exposed, and then we have categories of systems that are broadly understood to handle, Splunk is a log analytics solution, right? So the type of telemetry that you put into Splunk is logs. And Graphite is a time series metric system, so the type of telemetry that you put into Graphite is metrics, and so forth and so on. But it all comes from these events. So, event happens, the system logs it, now you have a line in a log file. The line in the log file obviously is not the event, it's a record of the event. You'll hear people talk about them synonymously, which is cool. People talk about, look at all these events in the log file. They're records of the events, that's fine. If you don't write all of the events to the log file and you just pick some of them out, you have a sample. If you aggregate them, for example, if you wait some amount of time and then you count the number of events and you stop your timer and you say there was 12,382 events happened during this second, cool, now you have a metric. That's an aggregation. If you start an event when, for example, a user request enters and you stop, now you have a start event and a stop event when the request is complete. And if you tie those things together and say they were related to the same user request, now you have a span. And if you relate if, for example, in the middle there, you call out to another service and now there's events on that other service that have a parent that points back to the original span that you were at the higher level. Now you have kind of a nested relationship of spans, and those are called traces because you can follow them through the system. And you can build call graphs and flame graphs and all of these kinds of things from them. But the events start it all, right? So this is all kind of stuff that comes from observing and recording events and then relating them together in some ways or another. But in any given domain, for example, if you look at like the open tracing project, it feels like tunnel vision sort of happens, which is perfectly fine. I mean, if you're in open tracing land and you want to be talking about spans and call graphs and all of those kinds of things, you really should focus your scope of discussion there so that you're not constantly referring to the whole landscape of everything that's going on. But it's good to just kind of pull back and see it from the 50,000 foot view, I think. So there's, as with any system, there's trade-offs in all of these kinds of things. So in any reasonably complex system, events are happening at a very high rate. And that's a lot of data, big data, again. The original big data problem, right? And a lot of these things, like metrics in particular, are actually responses to, wow, this is a lot of data. Wow, that's really costly just to figure out, how many requests we served in a second. It was 12,382. Hope I remembered my number. I get the same number? And so metrics, for example, are a way of turning an arbitrary, it doesn't matter whether your service is handling 100 or 12 million requests per second. A metric is just one number. So it's basically a compression technique. By aggregating all of those things, you get one number. The number may be larger or smaller, but it's just one. And that seriously limits the amount of storage that you have to consume bandwidth to send these things somewhere, storage to store them, compute and I/O power to aggregate them and make sense of them and do analytics on them later, et cetera, et cetera. So metrics are kind of the original thing since RRD tool, and then Graphite, and now Prometheus is kind of the hot new kid on the block. And metrics are great because they're really compact, and you can actually get a ton of valuable insight out of them, particularly if you choose your metrics wisely. But the criticism of metrics is that they're one-dimensional. And the response to that is often, as we see in the newer generation of monitoring systems like Prometheus, the response to that is often, well, we can add dimensionality to the metrics, like we can tag them. This metric came from a host, and the host is this size of EC2 box, so we'll put a tag of the EC2 size. So now we have not just a metric that's time-stamped and timestamp values over time, but it's tuples over time, and those tuples are attributes like it came from an x4 from an i4.x large, and those go along with those metric points. The problem is, even when you add lots and lots and lots of tags to metrics, you can't get back to the original events, which are typically very rich. The original events might often have 5 to 50 different kinds of attributes, depending on how you aggregate them and how many of them you collapse into one thing and call a single event. And it's very difficult to do that. It's really kind of impossible to do that with time series metrics. So you end up having aggregated away data that you often want later. So you want to slice and dice kind of arbitrarily. And a lot of the observability systems, which is why this is relevant, a lot of systems that are designed to help you make sense out of highly observable systems have very high cardinality, multi-dimensional slice and dice. You can drill in as deeply as you wish, all the way down to the original source data. And if you've aggregated things into metrics, you kind of can't do that anymore, even if you got highly tagged kinds of things. Yeah.
Based on kind of what you're seeing in the industry, what's the balance of where you call that trade-off to be worthwhile versus losing data? Right?
Yeah.
What is that middle ground?
Yeah. So the balance. So you've read the rest of the slide, so I don't necessarily need to read it to you. So why don't I skip ahead? So the compensations or the trade-offs that people will make is raw logs are really expensive. Actually, did I have a slide on this? Forget that, I didn't peek ahead. So raw logs can be a lot of data and can be really expensive. So your Splunk bill can be really, really high. So one of the trade-offs that you can make there is if you insist on storing raw log events or raw event data structured, is to sample it, to capture 1 out of every 10,000 or something like that, Now you have a sample of the population from which you can extract the original population or extrapolate the original population. The problem with this, of course, is that you do miss things. So if you have that 1 in a million error, and at Vivid Cortex we don't sample, we do a combination of sampling plus aggregating, so we're actually measuring everything, but not retaining all of the original raw data. And our sampling algorithm's really smart. So if you have that 1 in a million error, we'll actually preferentially sample that and keep that raw data. And what we found from doing that is that it's incredibly valuable to do so. So we found, for example, bugs in commercial off-the-shelf software that's been around for a really long time, and 1 in a million or 1 in a billion or something literally along those kinds of orders of magnitude would have a weird error. And if you were only sampling 1 in 1,000 or 1 in 100 or 1 in 10,000, you just would not catch those. And sometimes you really care about those things, especially when they're, for example, payments or, So there was a commercial off-the-shelf replication middleware that one of our customers set us up and found that there were some really weird things. And of course, those errors we're looking for, and we're sampling those errors individually and particularly. And so we were able to pull that out. But they were happening just so rarely that this software was 10 years old and nobody had ever found it. Sent the symptoms of this to the vendor. A couple of days later, they were like, oh yeah, we totally see where that's happening. They were trying to set a variable to a negative value, and it could only accept 0 and greater. And so we were able to find that by having the original data. But if you're just sort of blindly sampling, you miss that. So that's the trade-off of sampling. For metrics, a lot of times people will put a reasonable amount of dimensionality on things, but when you get sort of the full cardinality of, if you take a system like Prometheus, this was totally technically infeasible in the previous versions, but in the newer versions they fixed a lot of the technical limitations of the storage engine. But even in the new storage engine of Prometheus, if you put really high cardinality tags on things and you slice and dice, instead of just requests per second, it's requests per second for a user and an application endpoint and a controller and an EC2 size and a host name and all of these different kinds of things, you eventually explode the number of time series metrics that you have to the point that you have the original data set. So it's really pointless to try and use metrics for completely full drill down into the original source data. You should just store the original source data if that's what you're trying to do. So you kind of see this back and forth between the sides. The one side says, hey, cool new, they call themselves an observability service, but they're more of an analytics service that heavily advocates sampling and says that sampling is cool so that you can see everything. And the Prometheus people are going, you're not seeing everything if you're literally dropping 99.99% of everything that happens in your systems. And I see that from both sides. On the time series metrics Prometheus side, the downside is they're aggregating away a lot of stuff that you just can't get back. And on the other side, they're throwing away a lot of stuff that you're going to miss. There are a lot of systems that do no sampling. The systems that do sampling argue that you can't scale without sampling. They say it's technically infeasible not to sample. You have to sample. You're an idiot if you don't sample. I think that is sort of a marketing stance. There are lots of systems that don't sample. Heap Analytics. They have articles on why sampling is bad. Dynatrace. They've built their whole brand around don't sample, capture everything. You've got to be able to trace every user action, every transaction, end to end in the whole damn system, right? So there are systems, and Dynatrace and Heap scale. They certainly do. Amplitude, another analytics, front-end web analytics system. They take a very strong stance against sampling. So it can be done. The systems that do it have invested a lot in making their back-end storage efficient. And they solve problems for a problem space that metrics and sampling-based systems don't. So, kind of talked about this, but it was a good tangent. So there's tons and tons of stuff to instrument in a system. If you want your services to emit telemetry that makes them highly observable, where do you even start? I mean, there's hundreds. In many systems that are off the shelf, like MySQL, there are thousands or tens of thousands of things that are coming out of those systems that you could instrument and record for later analytics. So the question is, what should I, right? What's the most important? And of all of the different stuff, I like to kind of separate it into the quadrant, where what we want to do is the stuff that's most meaningful, is not repetitive. For example, things that are not highly correlated and shouting the same message over and over again. And the stuff that's very explicit, very explicitly tied to something that matters. Not like a cache hit ratio somewhere, or some obscure category of thing that you're not sure why it's there, except that the developer of the system, it was possible and so they did. But what are the things that are really actually valuable? And so kind of core principles for me are, instead of observing the service, let's observe the work that it does. We really don't care about the service for its own sake. It has no value, except in that it can do work for us. So let's observe whether it's doing its work well, right? And to understand and diagnose why it is or is not doing its work well, we do need to observe the service, but only for that goal of, not for its own sake, for the sake of being able to diagnose when it's not doing its work well, right? And on the raw event storage versus time series metrics, there is a handful of metrics that are true health indicators of any service that is request response oriented, which is the vast majority of what we're dealing with, that are really, really rich and can tell us a ton about that. So I want to dig into that a little bit. So when we kind of think, what should I, if I'm trying to build a service to be highly observable, what should I emit from it? This is an easier class of problems to answer than taking an off-the-shelf system like Apache or MySQL or something like that and going, wow, 10,000 things to measure, what should I measure? They've already sort of given you an opinion. They've said, here are the things that you can measure, pick what you want. Which kind of forestalls the question of, well, what if I want something that isn't in there? Kind of hard to notice the absence of something. It's kind of hard to look at 10,000 things and go, the majority of these things are uninteresting to me, which is why people will often scroll through dashboards and go, what do these things mean? There's a whole bunch of metrics. What does it mean when this thing goes up, the buffer pool goes down, and the cache hit goes, the other way? What does that mean? And that's really a question without an answer, because it's kind of the tail wagging the dog. So when we're building a system, we have the opportunity to start from greenfield and say, what should I build? What instrumentation should I build into my system to emit the kind of telemetry that's going to provide me really high value? And it's a great question. So there's a couple of popular frameworks. There's some formal methods. You've already read what's on the screen here. But there's these very well-established ways to analyze system performance, like queuing theory and so forth. And what I've done here is just kind of taken a census of what are the types of metrics that each of them seems to deal with. And there's lots of overlap. There's utilization in multiple places, there's requests in multiple places, there's duration or latency in multiple places, and throughput. And so there's a lot of overlap on these things. And actually, if you boil these things down, you get a really great set of metrics that can tell you tons and tons about your system. And when you do that, you get what I call the Zen of Performance, which is a kind of no blinders on, no tunnel vision, but holistic view of system performance that doesn't focus just on the workload. It doesn't focus just on the service and its resources down that's behaving. And if you think about it, when you've had performance problems, either you or people around you have often likely kind of dived into what they're familiar with. In my domain, customers, when I was a database consultant, always came and said, the database, things seem to be really, really terrible, but we can't figure out what's wrong because CPU utilization is fine. Well, CPU utilization is very much a system resource utilization metric. It has nothing to do with whether users are getting a good response or not, but it was the thing that was familiar to them, and they had been taught either consciously or unconsciously by observing or reading or whatever, or just the tools that are available to them, that if it seems like there's a problem in the database, you should go look at CPU, disk, I/O, network, all of these kinds of things, and see if there's a problem. There may be a problem. Customers may be really, really suffering, despite 5 nines or 6 nines of availability, despite CPU being low and no other apparent problems. There may be terrible problems on the customer's point of view. So if we get those blinders on and we look only at the system side, which is really common for system administrators to do, then we're going to miss the big picture. On the other hand, if we look only at the workload and what a user's experience is, we're completely missing obvious and really beneficial opportunities to optimize our systems and understand how they respond to this workload. So you really have to look at both of those together. And that's what I call the Zen of Performance, because it's all like, philosophical and, right. So you have these external and internal views, and I try and tie those together because you really can't understand the system without that. Because the system is not just the server and the software running on it, it's actually the population of users and their requests too. They're literally part of the system. So when we talk about a system, we need to be thinking about our users and their requests and how they impact each other. So if you've read, who's read the SRE book? Awesome. It's a great book. So the SRE book, it's also, by the way, it's available online for free, google.com/books/something, or I don't know. If you just search for Google's SRE book, you'll find that the whole thing is published online. And they introduced this notion of 4 golden signals to try and help people understand that there's only a few things that matter when you're monitoring a system or when you're building a system to make it very observable. And those golden signals are a little bit difficult to understand in some contexts. For example, they talk about saturation, but what does saturation really mean? To different people, I found that's really confusing a lot of times. So what I've done is I've kind of boiled this down into 2 acronyms. One is external and one is internal. So CELT is concurrency, errors, latency, and throughput. I would have put errors last so that I could put the first 3 first, but then it doesn't spell a word. So limitations of the English language and how many things you can make an acronym out of. And what I've done is I've named those the formal system performance method, broadly accepted names for those things, so that you can tie them to existing definitions. And when you're reading a textbook on queuing theory or something like that, you're not going, well, how does saturation tie into this? Because saturation doesn't appear in this textbook at all. So I've tried to name those things in ways that are broadly accepted and have specific singular meanings. And then use is the something that I've borrowed from Brendan Gregg. And together these are minimal but sufficient for a highly observable system. Let's call it a highly observable service. I needed to edit that slide. And how do you actually build this? So the foundation of this is a process list. Every highly observable service, without exception, that I have ever studied, has a process list. Your operating system has one, obviously. You can run top, and you're basically getting an updating view of the process list. Any web server worth its salt has one, et cetera, et cetera, et cetera. They all have some. And you can build one into your own service, too. They're always really similar. There's always, some concept of a worker within the system, and whether it's idle or handling something, there's a unit of something ready to do work. And if it's doing work, then there's the request itself. So the process list is the thing that holds these requests. And they always have, some text that's like whatever that request or command or whatever was. And then there's a state, and hopefully you get, in richer systems, you get things like the start time, or maybe just a total time elapsed in some systems. And from this, you can start to get a lot of information about the work that the system is doing. We built one of these into our API and service layer at Vivid Cortex, and it was really easy. Our service layer is entirely written in Go, and I wrote this. I'm sure that the engineering team probably regrets that I wrote it, but I wrote it early on, and it exposes an HTTP API, so you can query what is running across all of our services, anywhere on any of our servers, what's in flight right now. And from that snapshot of right now, and from the history that this little thing, which is not very much code at all, keeps inside of it, you can start to get those time series metrics if you want to put them into a metric system. So you can aggregate a process list, right? So it's really foundational. And I just said all of this. Well, I said all of it except that state changes to individual processes or events, and you can emit those things into, you can aggregate them into time series metrics, but you can also emit them into logs, you can emit them into other systems to aggregate them. You can start and stop spans, et cetera, et cetera. So you can make it as sophisticated as you want, but if you start with a process list, you can pretty much make your system arbitrarily observable. By aggregating these things into those CELT and use metrics, you can get tons and tons of insight into what's really happening in your systems. Even at a fairly global view, a single metric can unpack surprising amounts of power, specifically when you start to look at the relationship between metrics. So just for a couple of examples, Linux's proc diskstats is an aggregation of all of the disk I/O events that go through the I/O service layer. And they instrument it at a couple of points where you can see where things enter the system and when they enter service after they've been waiting for a disk to be ready to service them. And I wrote a blog post about this. I should have put the URL up there, but if you search for how Linux's proc disk stats works, or how Linux IO stats works, you'll probably find on my blog, which is XAPRB, the same thing as my Twitter handle. And I kind of dug into how these metrics can actually reveal a lot about the stuff that was aggregated into them. So from the relationship between these metrics, you can actually kind of disaggregate and figure out a lot of what was going on. So here's some of the stuff that you can figure out. You can, from the average queue size, that is the waited time per interval. You can read the disk stats kernel documentation. And from this, you can calculate all of these kinds of things, like the service time, that are not possible. There is no metric in the disk stats instrumentation for service time, but you can calculate it. And service time is typically something that people would give their right arm to get, because most systems don't expose a service time directly. They'll expose an end-to-end latency, but the service time is, if you subtract the queue or wait time off of that, the service time is the time spent actually doing work. And that's something that's really hard to find in a lot of systems. But with these couple of metrics and the relationship between them, you can actually get that out of proc disk stats. You can also look at these kind of non-linear relationships. Linear relationships are really boring. They don't tell you very much. But if you look at the curve of non-linear relationships and figure out where you are on those curves, you can derive a surprising amount of insight between them. There's the universal scalability law, which tells us how things get bloated as they get more heavily loaded, and it says as they get more work within the system, they spend more work doing kind of housekeeping and coordination and other kinds of things, and they spend less time actually doing the work, which is why every benchmark that you ever see that has a number of threads along the x-axis kind of peaks and then it dips again, because the system gets too busy and it actually can get less work done when you overload it. The universal scalability law describes why that happens, and again, that's just a relationship between two really easy to get metrics. So you can unpack these things and get lots and lots of insight between them. And I wrote some ebooks on these things. They're on the Vivid Cortex website. They're also on an ebooks repository on GitHub if you don't want to, put in your work telephone number and get a call from a sales rep. Not that any of my favorite sales reps wearing striped polo shirts are in the room. But if you're not interested in buying Vivid Cortex and you just want to learn about this stuff, it's there. So I think that's pretty much everything I've got. Highly observable systems help you to figure out what is going on in your systems, whereas monitoring will tell you when a system is broken. Observability will help you to ask and answer questions about why it's broken and what's really going on. And to do that, you need to monitor the work, measure and record the work that those systems are doing. That's much more important than CPU activity or things like that, which are just symptoms of the work being done, much like your fever is a symptom of your virus, And every service, ideally, should have a process list because it's so low effort and so high value, in my opinion. And then, you've got these trade-offs, so you have to pick your systems. The tools are real, and if you don't have good tools, you're not going to be able to get good results. So obviously that's why I'm in the monitoring, or more properly, I guess, analytics business, why I founded a workload analytics company so that you can really slice and dice this high-frequency workload data about your database servers in our case and figure out what the hell they're really doing and why. Those are questions that you can't answer unless you're capturing all of that data, unless you have good tools to help you make sense of it. Because the slow query log across 100 servers at 80,000 queries per second per server is nobody's friend, right? So great tools help. Standard tools like just Prometheus or Graphite or any other time series metrics tools, if you choose your metrics right, they can give you killer bang for the buck. If you just shove stuff in there and now you have 10,000 metrics, you started with one problem, now you have 10,000, right? Always happy to chat on email or answer questions now or whatever. Love talking about this stuff. Yeah.
Can you talk a little more about, you touched on earlier that a lot of the logs, or a lot of your metrics could be the same and you're trying to tease out that 1 in a million or 1 in a billion. How would you achieve that on the ingestion layer, I guess? And how would you ignore everything else and look for that one?
Right, how can you look for the 1 in a million, the outlier, the thing that's really important? Actually, there's another ebook on Vivid Cortex's website about that, about probabilistic sampling from a stream, a really high frequency stream of very rich events. The way that our agents do it, I mean, we describe all the algorithms and math in there, but the way that our agents do it is basically we kind of start with, we're going to break this stream down into categories. So we do complex event processing in real time on this stream of query request events that are coming into the database server. We categorize them and we say we'd like to keep some from every category. So you can't just like globally say we want 1 in 10,000 or 1 in 100 or something like that, because what if the workload is mostly one kind of query and just very occasionally this other kind of query? You're going to miss all of those. So we really want, we actually want less samples of the high frequency kinds of things because they're mostly repetitive, right? So we want proportionately more samples from the rare kinds of things. And we want proportionally more samples from things that are interesting because they throw an error or because they're high latency or those kinds of things. There's a handful of dimensions that we say make something more interesting. And then from there, it's basically just a math problem to figure out how to do this in finite time and space, which we do with some approximate sketch algorithms, fairly well-known stuff like a variation on the count min sketch. So for each category of events, we want one at least every X amount of time, and there's some probability to get that right, which we got wrong at first and completely DDoSed ourselves. But after we kind of figured out the right way to think about the probabilities, it was pretty easy.
So you're doing like variable sampling based on some buffer somewhere that looks at everything and samples some at a higher rate than others.
Yeah, actually we don't even buffer things. So that's the really neat trick, is to be able to sample things without buffering anything. You look at an individual event totally in isolation, and the only thing you know from the sketch is when was the last time, maybe more or less, that I saw something like this. And we have an exponentially decaying probability. We actually make it linearly to make it faster, but basically for every event you go, I should sample this with a probability that is determined by how long it's been since I've seen one of these before. So if it's been a long time since I've seen one of these before, definitely sample it. That way we sample low frequency, rare things with a higher rate. And if it's not been very long, then with a small probability we sample.
Storing all those locally before sending those events out. Those tables are the references of timestamps.
The sketch is basically kind of an array of arrays, and we store that locally in the agent that's doing this complex event processing. Everything else is being phoned home in real time to our SaaS platform.
If it makes it out, then it stays.
If it makes it out, then it stays, yeah. And what we do with the rest of it is we aggregate it into really high dimensional time series metrics. So we'll occasionally pick out an individual thing and remember everything about that, and the rest of it we put into metrics, which are much more compact. There was another question right behind.
Yeah, I was saying, I like some of the definitions you use, particularly around monitoring, being a verb, etc. I think that's a good point to hone on. I think one of the things that we do on some of our platforms is we give less attention to the event classification or the metrics classification for alerting rules and things like this. It seems to be sort of the last thing we think about. We put a lot of effort into collecting the metrics, putting them through a pipeline, getting them into expensive storage systems. But it's that sort of, I have my data, but I actually have my actionable, let's say, intelligence that I derive from that. I'm guessing that you probably run into those sorts of things too, where at some point you've got to, sort of take that huge volume of data and say, I'm just going to make a yes or no decision, or a red or green decision, or some other continuum that's been, let's say, reduced, right?
Yeah. So I'll repeat your question for the recording because I don't know if it's picking you up. But so basically, your comment is about working really hard to generate lots of metrics and store them, and then being like, well, what do we do with these? Like, which of these are actionable, and how do we make decisions about service health and whether we should page somebody, which is a super common problem. And some folks that I know came up with a really neat solution to this that I think is super elegant. Basically, it's let's go back to the RED method, requests, errors, and duration. This comes from places like Twitter and what's the name? Weaveworks kind of coined this acronym as a reduction of the 4 golden signals, because one of the golden signals was really kind of vague and they didn't think there was very specific. But these things are request scoped and very specific. The acronym, I think, is a little bit forced to make a word out of something. So the requests, rate, errors, and duration. Duration is what I would call latency. That's a more commonly used term for duration or service time. And the request rate is more commonly called throughput. But those 3 metrics, the error rate, the throughput, and the latency, are really great signals of service health. And so if you have 10,000 or a billion or whatever metrics, and literally some folks do have a billion metrics, and you're kind of drowning, this is a really great place to start. And the philosophy that came out of this was they have this, have you seen those Death Star diagrams where there's like a circle and all of the services are around the edge of the circle, and there's a cord drawn between each of them that communicates, and the whole thing looks like a spaghetti or a beautiful data visualization, but there's lots and lots of lines connecting them. In a highly networked, service-oriented architecture like that, you probably have dependencies of which you are a customer. So, if you're making a call out to another service, you are that service's customer. And if your service appears to be having trouble, you have an immediate question: is it me or is it my dependencies? And there's a hierarchy or a call graph of these service dependencies that you can traverse to ask, are all of my dependencies healthy? If they are, then I'm the problem. And so how do we determine healthy? Well, these 3 metrics are a really good way to do that. I argue that by putting concurrency in there, which is a metric of load, even though you can use Little's law to calculate it from the other 2, it's good to have in and of itself. You can get better, but still, just these 3 metrics are great. So you can look at any service. The philosophy in these places is that you can look at any service and you can know whether it's healthy by looking at the throughput. So you can see whether throughput is steady, has dropped, or has climbed over time. So you can answer questions like, am I receiving an unusually high rate of requests? You can look at the error rate. So am I throwing more errors than I used to as a proportion of the throughput? And you can look at latency, particularly long-tail latency like 99th percentile or 95th percentile, to answer, am I overall or for some portion of my workload responding much more slowly than I used to? And so those 3 signals alone can tell you this thing is working well or it's not. It's basically quality of service metrics. If this service is giving good quality of service to its customers, whether those are users or another service that's calling it, then all's well. If not, then you have to ask, is it the service itself or is it any of its dependencies? And the genius of this is that you don't have to have internals knowledge of any of the dependencies. You can traverse to the others and you can look at their dashboards, and you now have this universal, completely grokkable, instantaneous dashboard or set of metrics on every service, no matter how many, no matter where they're hosted, no matter who wrote them, no matter what the internal logic is. You can tell whether or not at a glance they have caused the degradation of service that your service may be experiencing. So does that make sense?
It does, and you mentioned something that implied maybe some of these things could be learned. So for example, if you look at something like latency, I need to interpret and have a hard-coded threshold, or it sounds like we can learn like what a latency anomaly would look like.
Yeah, so does latency, do you have to have any context for the latency to decide whether it's good or bad at a moment in time? So that's why people like to use time series charts, of course, so that you can widen the time range and go, this thing seemed to be okay an hour ago, so let me widen to an hour and see, did it go up? Was there a cliff or something like that? It's actually something that we're working on at Vivid Cortex right now to let you look at a narrow time range and answer a question, is this typical? So we have really spiky workload in some areas, very smooth in others. Typical services have this as well. Cron jobs run at 8 minutes past the hour every hour. And if you're just looking at, from the hour to 20 minutes past and you see this big spike at 8 minutes, it's like, well, if I didn't know the system, I wouldn't know if that was typical or not. So there's a couple of different ways to do this. The go-to solution that a lot of people kind of jump for, and I give a talk at Influx Days recently arguing it's not great, is anomaly detection. Anomaly detection is kind of a Pandora's box that seems like it's going to solve all your problems, but it has such a high false positive rate that for most people it's not the right answer in my view, unless it's constrained to very specific use cases. And we use anomaly detection and all kinds of other buzzwords at Vivid Cortex, but only in very specific use cases where we know they'll give good results. A much better thing, I think, is actually to draw typical bands. So instead of having a single metric, just drawing a line and you go, well, is this normal? If you have typical bands drawn around things, you can answer that. If those bands just go straight across and your metric goes like this, your answer is obviously no, it's not normal. But you can also tell just by looking at something whether it's, whether it's climbed too high, or if you have an SLA that or SLO, service level objective, that you should comply with, 99th percentile, lower than 30 milliseconds in every 5-minute interval, you can know whether or not you're violating that. So a variety of ways to evaluate that, I think. Good stuff. More? Yeah.
So how do you stay excited about analytics and observability, and how do you infect the people around you to get them excited?
How do I infect people around me with my excitement about observability? Do I? I don't know. I guess it just comes from the heart. It's interesting. I think in probably right about 10 years ago, there was an intern at my office, and we were walking to lunch one day, and she said, "Why do you love databases so much?" And I was like, I have no earthly clue. And I still don't really have an answer for that. I mean, I just do, And why do I love observability? I think I love solving problems for people. And, my career as a consultant was often really ultimately simple problems when you could focus people on measuring the right things. And a lot of times people would come in with a problem that had been bothering them and causing impact to their business for 6 months or something. They had brought in experts, they had all of their best people, they had upgraded systems, they had reconfigured, they had switched to different databases, they tried everything. And my method was always the same. Okay, let's measure the work. And I built a whole toolkit around that. It's now called Percona Toolkit. I was working for Percona at the time, and I eventually renamed it Percona Toolkit. And it became really useful. I eventually kind of, it started out being able to do a zillion things. It can still do a zillion things, but if you run it with no command line arguments, it does the one thing that's most valuable, which is it looks at the workload and aggregates the most time-consuming queries and puts them to the top. And all we had to do, and I would say 19 out of 20 cases, was do that and then have a discussion with the engineers. And halfway through the call, the engineers would go, I got it, I'm dropping off the call, bye.
So are you always coming in when there's a problem?
In most cases I was. In a lot of cases, people were calling me in to be like, we expect a big spike, we need to make sure that we're architected for this, blah, blah, blah. But a lot of times it was more reactive, like, we're pulling our hair out, nothing has worked. We feel like our vendor is kind of gaslighting us and telling us that we need to see a psychologist, And it was almost always solvable just by measuring the workload and going, well, let's talk about these top 10 things. And people would go, huh? That shouldn't be the top 10. And that's kind of the experience that people have with Vivid Cortex too, because you install, the installation's really simple. A couple of minutes later, you're looking at the top 10 things, again, by total time consumed, and they go, why is that thing so spiky? It should be smooth. Or, what the hell? Where's that coming from? Why is our top query select 1? Things like that. So as programmers, we build things and we have this mental model of how the code is supposed to work. And we figure out that that's not the case because we write tests and tests fail and we're like, oh, my mental model was wrong, let me go fix it. And then the tests don't catch everything, so we deploy it and it's still behaving weirdly, so we debug it and we're like, the mental model was wrong in even more subtle ways. And then we're satisfied. But then the database performance problems happen because we also have a mental model of how this thing is interacting with the database, which is basically invisible and unmeasured in the vast majority of companies. And our mental model about that is, surprise, surprise, wrong also. So, my motivation was always kind of like help people stop the suffering, because it's very stoppable, right? And that's why eventually, when I got tired of sort of Groundhog Day of doing this over and over again, I was like, I really want to write a product, want to build a company around this. So I founded Vivid Cortex. Yes?
For transaction systems, the queuing theory usually just assumes the value is only achieved at the event that the transaction is completed. If I'm trying to buy a ticket until I actually see the Ticketmaster confirmation screen that I bought the ticket.
You don't have a seat to go see Bono.
But in other sort of human user situations, there can be value achieved before that. To take some long-running examples, Uber shows you that the driver is coming for you, and you see how far away he is, and you see his name, and so on. Pizza Hut shows you how the pizza's being made and how close it's getting to you. But even in a web page, time to first paint, or using progressive images conveys that you're making progress, even if then it crashes.
So end-to-end request response completion is not the be-all and end-all.
So what if you had a feature that would improve time to first paint, but actually reduce the overall time?
It's possible, yeah, it's possible. Yeah. One of the things that we do at Vivid Cortex is we measure, we observe network packets. And by default, the way that we measure the latency of a query is the time from the last packet in to the first packet out. So it is kind of the database's time to first paint, if you want to call it that. But a lot of queries that may send a large amount of rows, such as the easy example is a backup that's just selecting all of the rows from a table. Those things may run for a very long time after that first packet, right? So it's not cut and dried. The analytics on that gets really, really messy. I think someone else, you had a question.
Do you have people coming to you looking for help analyzing systems, not strictly for problems with performance, but perhaps with fraudulent performance or signs of intrusion? You mentioned anomaly.
It's a great question, yeah. A lot of our customers come to us with performance needs first and foremost, but then they ask us for help with, or they ask, could we build queries to, intrusion detection or fraudulent activity, or could we, there's the sampling functionality is actually very sophisticated and has a lot of customizability. So some of our customers have had kind of Heisenberg bugs in their systems that they couldn't explain. One of our customers basically came to us with a problem that had been going on for months of some data changing that wasn't supposed to be touched anymore. They had, deprecated all of the systems. They were trying to break a monolith into pieces, and they needed the piece to go completely quiet before they were confident that all of the workload was going to the new thing that they had broken out. And yet this old data was changing and it wasn't supposed to, and they couldn't find anywhere in their code base, and they were grepping, and the solution to this, because it was really high volume systems, turning on logging was basically an outage because of the volume of activity on the systems. So it would take them months to get answers to what is still changing data. And with Vivid Cortex, we were able to build in a thing that said, instead of probabilistically sampling, if it matches a pattern, a regular expression, just nail the first 100 of them with 100% probability. And 100 samples of something changing data in this table ought to be enough for us to go and figure out where this is coming from. And sure enough, we just let it run overnight. Next morning, we looked in and searched for that table and found the first 100 samples and inspected those samples. And I mean, they had their answer with 30 seconds of work. So we get lots of those kinds of things. And there's lots of potential for us. A lot of our customers are very unhappy with the solutions that they're required per their security compliance requirements. So, we just achieved SOC 2 compliance, and so I feel their pain too. A lot of times they're required to have auditability on things, but the auditing systems insist on capturing 100% of activity, which has, in the words of one big customer, nauseating overhead, because most of that is just like, pin a photo, pin a photo, pin a photo. It's like 99.99% of what they're paying these vendors for is pin a photo, pin a photo. It's not, the database administrator left his terminal open and somebody came and started doing nasty stuff in the database. So there's some kind of obvious low-hanging fruit there. But for the moment, we're still really focused on being the world's best database performance management and analytics solution. So we've really focused on that, although there's certainly long-term potential for a lot of these other things. Yeah?
So between the use method and the foregone signals, saturation comes up, and I'm assuming that when you alluded before, the one signal that has a very arbitrary thing, that it was saturation, because I feel like it is quite hard to define.
Yep.
It's clear from the Brendan Gregg's perspective of the CPU run queues versus the actual CPUs in the system, stuff like that. But have you at least personally come up with models on like how you would equate saturation to holistically like a system? Like, is it somewhere related to like what you might find in universal scalability law? Like, how do you actually quantify saturation holistically across?
So Brendan, it's a great question. What does saturation mean? And Brendan has a pretty good definition of it on his webpage, which is why I used it. Otherwise, I think I would have chosen a different word. Although it's difficult to think of a word that kind of encapsulates this. So utilization has a very specific meaning in performance. It's the portion of time during an observation interval when the system is busy. And we shouldn't use that for like disk utilization is 99% full. That's a different measure, and that should be more like available capacity or free space or something like that, rather than conflating it with utilization. Saturation can be a little bit nebulous as well. And so what I think about saturation is, given that utilization is off the table, when you think about things like the I/O bandwidth of a disk, or of a network interface or something like that, they have a fixed amount of data that can flow through them. And throughput is also off the table. So 200 megabytes a second shouldn't be considered throughput, because throughput is a rate, not a volume. So saturation is the only other word that I've seen people use in a fairly well-defined way to refer to the volume as a fraction of the maximum volume that can flow through a system.
And so, sorry, just to bring it back again, like, so
Yep.
holistically, like, do you find that you could possibly derive saturation based on something like, I guess I'm gravitating towards like universal scalability law, because there is some sort of inflection point that at least tells you some rough maximum amount of work that can be accomplished, and even though you can still do more work and get more concurrency, like that seems like it's maybe a good starting point for sort of holistically, like how much you actually have there and how close you can get to it, and thus your saturation. Does that sort of, I guess, mathematically fit, or am I off, or is that a good place to start?
It does. I think of the universal scalability law's inflection point as the maximum capacity of the system. And you can think of maximum capacity as the maximum throughput or the point of concurrency at which you reach maximum throughput. Or you can think of it as maximum throughput or concurrency at which your response time SLAs are not violated, which is going to be somewhere to the left. And so if you're looking at these charts, off the side of the page, this chart is going to dip and go negative. You're going to get retrograde performance as you continue to increase load going to the right. And the point at which you peak out is definitely the highest throughput that you're going to get, and it's definitely the highest concurrency at which you can operate to get that throughput. But really, your maximum capacity is somewhere down the curve, to the left, to the bottom left corner of that. And that is there is a nonlinear gradient as you approach this operating boundary of load, because what we're really looking at in the universal scalability law is load in this sense. And as you approach that point of load, things start to just get really flaky, and you start to see systems. The pendulum starts to swing wildly. Something changes a small amount and performance changes a large amount. And this is what happens with queuing theory too. As you get close to that, close to 100% utilization, the hockey stick curve gets extremely sharp. So there's this operating boundary, and as you approach it, the system basically starts to push back at you. And it's an interesting question how you can see that coming and whether you can model that. And I gave a couple of talks over the last couple of months. There was one at Velocity in London where I talked about this, and another, I basically repeated that talk at LISA in San Francisco, and the LISA talk is on YouTube. So, I was trying to explain that, as you approach this operating boundary, the system kind of adapts and pushes back at you and tries to adapt you away from it.
Thank you. All right, so we're over an hour, and I usually try to
All right.
at that point.
Thanks for indulging me.
Yeah, no, it's not we who are indulging you. Thanks so much for coming, everybody who has come, and thanks for coming to speak. I always feel like when I hear you speak, there's this huge amount of clutter that's just cleared away from my brain.
Oh, I was going to say it was the opposite.
No.
I put a bunch of clutter in there.
So thanks so much. Well, I'm going to hang out a little and have another beer, so you're certainly welcome to stay and hang out with me. But let's call the formal part of the event.
All right, sweet. Thanks, everyone.